Okay, here is the plan coming up this week and moving forward. We are going to finish out Chapter 5 this week with trigonometry and trig identities and that kind of stuff. Today and tomorrow we're going to look at sum and difference identities, okay, and why we would use a sum or difference identity, what they are, how you work with them, that kind of stuff. We'll get into that today and tomorrow. Wednesday, Thursday, we'll get into the last section of this chapter. Friday, Monday, then, will be review days. And on Tuesday next week will be your Chapter 5 test. Okay? So just as a heads up. I mentioned one of the other classes, Mr. Strick and I were talking last week. And in terms of like the beginning stuff that we were dealing with the identities and all that kind of stuff and being able to prove them and work with them, the plan we're going to revisit tomorrow. But there will be one, at most two of those on the test. Okay, so there will only be one or at most two where you'd actually have to prove the different trig identities. Okay, something along those lines, where you get the left-hand side equal to the right, that type of stuff. So just a heads up, there will not be a ton of those on there. A lot of what that was for was getting you used to different things that we're now using. So, but today we're going to focus on, like I said, what are called sum and difference identities. So if you look on your formula sheet, it's number 5, it's below your unit circle there. The idea is we're going to take the sine of the sum of two angles or the difference of two angles, cosine, tangent, and we'll talk about when we would use these in particular, or why you would want to use these different identities. Okay? So with that being said, here's the first question of the day, and kind of the first example as well. What is the sine of 15 degrees? And we're going to get an answer that's going to be an exact value versus type it into the calculator and write down what the random decimal is. Okay, we want to get an exact answer. Just like on the unit circle, you got like square root of 2 over 2, square root of 3 over 2. Those are exact answers. What's the issue with the 15 degrees, by the way? It's not on the unit circle. That's a problem. That's where the sum and difference identities come into play. Okay? And so the question is, we can come up with 15 degrees by using some values that are on the unit circle. How can I get 15 degrees out of some of the angles that are on the unit circle? We could do 45 minus 30. So instead, we're going to actually do the sine of 45 minus 30. We're going to look at it that way instead. And here is where the identities come into play. In this case, we're doing a difference identity for sine. We're looking at this identity right here. So U and V in that identity, just as a quick heads up, U is just the first angle, V is just the second angle. Okay, that's all that is. So what we're going to take a look at is, if we do the sine of 45 minus 30 degrees, we're going to start with using our formula, okay, and just make sure the signs and all that stuff are correct. We have the sine of U. What that means is the sine of the first angle, sine of 45 degrees, times the cosine of V, which is just the second angle. Then if we keep working with that formula, minus the cosine of U, the first angle, times the sine of V, the second angle. Okay, and like I said, what we're going to try to come up with is an exact answer. So we're not just typing in stuff into the calculator and writing down to kind of a random decimal. Well, now, there's our identity. Okay, there's our difference identity written out. Now we just go through and start getting some answers here. Everything that we just wrote down is on your unit circle. So sine of 45 degrees, what is the sine of 45? Somebody said it. Square root of 2 over 2. So that's the square root of 2 over 2. Times cosine of 30 degrees. What's cosine of 30? Somebody said it again, I think. Haley, was that you? Square root of 3 over 2. Yep. Minus cosine of 45 degrees. Square root of 2 over 2. Times the sine of 30 degrees, which is 1/2. Okay. So we kind of reworked the problem a little bit so that we could end up getting some different answers. And now at this point, now we're going to basically clean everything up. Okay? A couple of reminders. When you've dealt with fractions a lot, so I shouldn't even need to necessarily remind you of this one. But remember, when we're multiplying fractions, numerator times numerator, denominator times denominator. Second thing, when we're multiplying radicals, you just multiply the numbers underneath. Okay? So in this case, when we multiply these first two, I end up with the square root of 6 over 4. Okay. Minus, when we multiply numerators, we get square root of 2. Denominators, we get 4. And now if you notice, you already have a common denominator. So I can put those two together as one. Here's a second reminder about radicals. Whenever you're adding or subtracting radicals, they act just like variables. You can't combine them unless they're exactly the same. So in this case, the only thing I can do is write it as the square root of 6 minus the square root of 2 all over 4. And now as you take a look at some of these different angles, like in this case, the sine of this, so that is the answer for the sine of 15 degrees. And now you can kind of start to see why 15 degrees is not on your unit circle. Okay? Or 75 degrees, or things along those lines. Because these are the types of answers you would have for your x and y coordinates. Okay? They're a lot messier than the average. Okay? But that is what the sine of 15 degrees equals. Yeah, Nate?
Will we ever have a sine of 13?
No, you'll have, that's a good question. You will always have something that you can use the unit circle angles, to get the non-unit circle angles. Okay? So you wouldn't have like a 13 degrees, for example. Okay? So that's kind of the warm-up in terms of here's how we use it and here's why we use it. Okay? Here's why we do the sum and difference ones. So then the next question that I have for you is this. We said it's a difference. We did the sine of 45 minus 30. Is that the same as if I just took the sine of 45 minus the sine of 30? Do we get the same answer or not? Let's take a look. Okay. So here's kind of example number 2. Rather than having to use the formula, can I just take each angle separately? So in this problem, here I don't have to do anything other than get some answers and see what we come up with. Sine of 45, square root of 2 over 2, minus sine of 30 is 1/2. And if we go through and we put that together as one answer, we end up with the square root of 2 minus 1 all over 2. Did I get the same answer? No. And so the point I'm trying to make in this example is that when you have something that looks like this, the sine of 45 minus 30, you can't take the sine of 45 minus the sine of 30. You can't just split it up. It doesn't work. You don't get the same answer. Okay? In that scenario, anytime it's a sum or a difference of two angles, that's where you need to use the identities. Okay? Use the formulas. Okay? With me so far? Doing okay? All right. Let's just do another one for some practice. How about this one? Cosine of 2 pi over 3 minus pi over 6. So, same thing. Let's take a look. Let's actually use this as a difference identity for cosine. So again, if you look at your formula sheet, the cosine and the difference identity we have cosine of u, which is 2 pi over 3, times the cosine of v, which is pi over 6. Be careful, make sure you get the signs right in the middle, okay? So then we have plus the sine of u times the sine of v, the sine of each angle. So sine of 2 pi over 3 times the sine of pi over 6. And just like the last one, now I've got a whole bunch of stuff that is on the unit circle. So now I can start to get some answers and clean those answers up a little bit. Cosine of 2 pi over 3 in this case, negative 1/2. Cosine of pi over 6, square root of 3 over 2, plus sine of 2 pi over 3, is the square root of 3 over 2, plus the sine of pi over 6 is 1/2. And we clean things up now. Multiply the fractions, common denominator, put it all together as one final answer. Here we end up with the negative square root of 3 over 4 plus square root of 3 over 4. Ultimately, in this case, what do I get for an answer? We end up with 0. Those two cancel out, and we do end up with 0 in this case. This is one of the few times. Most of the answers you're going to see will be like that last one, square root of 6 plus square root of 2 or minus square root of 2, those types of problems. Anybody tell me why this is 0? In this scenario, I would normally not use a sum or difference identity. Anybody tell me why? Yeah. If you actually took these angles and figured out what angle was I working with, if you actually did the difference right away, common denominator would make that 4 pi over 6. Minus pi over 6 makes it 3 pi over 6, which is pi over 2. What's the cosine of pi over 2? 0. It's already on the unit circle, so it just confirms what we already talked about. Like I said, this is not one of the scenarios where you would normally use this because it's already on the unit circle. This was mainly just practicing the formula, okay? And seeing that we really got the exact same thing. Okay, let's keep going. What if I gave you a problem like this? And we're not actually going to do all of those. We'll do 2 out of the 3. We'll either do sine or cosine, and then we'll do a tangent one, since we haven't done that yet. So I will tell you on this one, 11 pi over 12 is not one of the things that's on the unit circle. What makes this problem difficult? If I was trying to find the sine of 11 pi over 12, what makes this difficult? What do you think we should do first? What's that?
Find a way to get 11 pi.
Okay, so we got to try to find a way to get 11 pi over 12. Can I add some angles to get there? Can I subtract some angles to get there? And it's a little bit harder because we're in radians, right? Because of 11 pi over 12, it's a little bit more difficult to try to figure out which radians we have that either add or subtract to that. So what do you think might be the easiest thing to do first? Yeah, how about we change that to degrees instead? Remember how to change that back? What do we multiply by? 180 over pi. We got to get rid of the pi's and go into degrees. So that's where I'm going to start. Let's take 11 pi over 12. You don't necessarily have to do this, by the way. If you can figure it out in radians, that's fine. I just think it's easier if you do it in degrees. And I'm going to multiply by 180 over pi, our conversion factor, if we will. Pi's will cancel out. And now you do the math. 11 times 180 divided by 12. And what do we get?
165.
Should get 165 degrees. That's the angle that we are working with. Okay? There it is right there. 11 pi over 12 is really a 165 degree angle. Now it's a little bit easier to go to the unit circle and start to say, all right, now let's see which angles can I either add or subtract to get 165. And what do you think? What'd you say? You could do 120 and 45. Would work. Could do 135 and 30. That would work. Okay? So and I'm actually glad you guys came up with two different answers because you get to the same thing regardless of the combination you use. Okay? So it doesn't matter whether I use 120 and 45 as the two angles, or if I use the 130 the 135 and 30 as the two angles. I'm going to use the 135 and the 30, okay? Yeah, like I said, it does not matter one way or the other. That's just what I had up here. So let's say we use that instead. And we'll do a sine one. So if we take the sine of 135 plus 130, or plus 30, excuse me. That's what we're actually taking a look at. Try this one on your own. I'm going to see what you can come up with. Write it out, and then start to evaluate it. See if I'll give you a couple of minutes here to see if you can get the exact answer for the sine of 165. So here's the formula and the kind of the evaluation so far. So again, if I'm looking for the sine of 165, it's the combination of, there's one combination that'll get me there, that we do have angles. Here's just setting up using the sum formula. Here's evaluating all of those four different values. And then if we finish this up, you should end up with, when we multiply, we get the square root of 6 over 4. Second part, we end up with negative square root of 2 over 4. And when we put that all together, we're going to end up with the square root of 6 minus the square root of 2 all over 4. Okay? So there's the sine of 165 degrees. Okay? Like I told you, there's what most of the answers are going to look like. Some version of the square root of 6s and square root of 2s and all that kind of stuff. Okay? Let's do one more, only because we haven't done a tangent one yet. So let's take a look at a tangent one as well. So let's do the same problem, but now with tangent. Tangents, what I will tell you in advance, they get a little bit messy. Okay? They get a little messy on these. Good news is I think I only put one tangent problem. I shouldn't even say I think there is only one tangent problem basically on your one or two on the assignment. Okay? So you won't have a ton of these. So same thing. We break it up into our two angles, and now let's use our formula, our tangent. In this case, sum formula. Tangent of the first angle, 135, plus tangent of the second angle, 30, over 1 minus tangent of the first angle times tangent of the second angle. All right, so that's the setup. Now we evaluate, just like we were doing before. You actually get answers for all those different tangent values. So tangent of 135, in this case, we have as negative 1. Plus the tangent of 30, we end up with, it's 1 over the square root of 3. I'm going to rationalize the denominator right away. So I'm going to write that as the square root of 3 over 3. Okay. Over, we have 1 minus tangent of 135, we just said was negative 1. And tangent of 30, we said was square root of 3 over 3 when we rationalize that denominator. You see where it's starting to get messy already? Now we've got radicals with fractions inside of fractions, okay, which are called complex fractions. So now we need to kind of start working our way through and cleaning this up a little bit. And there's a couple of ways you could go about this. They're all about kind of equal in terms of difficulty level. I'm going to go back to what you had done when you were working with trig identities. If you had a problem like this in general with trig identities, where there's fractions inside of fractions, I'm going to get common denominator in the numerator and combine those. So instead of that being -1, I'm going to rewrite that as -3/3. That way now we've got a common denominator. So I'm going to put that together. We get -3 plus the square root of 3 all over 3. That's the numerator. That's the top part of our tangent problem. You put these two together. -3 plus the square root of 3 over 3. Now we work on the denominator. Same kind of idea. Quick heads up in the second part, if I'm going to have -1 times the fraction, just makes the fraction negative. But what happens if you're subtracting a negative? It's positive. So really that -1 kind of goes away, and this is really just 1 plus. Okay? Because you're subtracting a negative value, so it changes into a positive. So same idea that I did up on the top. I'm going to take the 1, we're going to change that common denominator, make that 3 out of 3. And now we'll combine terms in the denominator. All right. So it's a little nicer. Not much, but a little bit. What happens now? What comes next? Anytime we divide by a fraction, multiply by the reciprocal. Okay? So instead of dividing by this fraction, I'm going to multiply by the reciprocal of that fraction. So get rid of that, and now we're just multiplying two fractions. Okay? It does clean itself up a little bit. Okay? The fraction cleans it a little bit. Because that 3 and that 3 we can cancel out. Can I cancel the other 3's or the other square root of 3's? Why not? It's because they're terms, not factors. If you're going back again, if you're thinking about the trig identities when we were doing that, trying to figure out when you could cancel those identities versus not, -3 is a term, it is not a factor. Square root of 3 is a term, not a factor. Yeah.
What if they were both positive?
You still couldn't, because it's for the same reason. The sign doesn't have any, well, if these were both positive, is that what you're saying? Like this whole thing was positive and that whole thing was positive? Then the whole things could cancel. Then you could look at that as a whole factor. But you couldn't cancel like each individual part. I couldn't cancel the 3's, cancel the square root of 3's. You'd have to look at it as a whole thing. Okay? So when we write this, when we put this together, in our numerator we have -3 plus the square root of 3. In our denominator we have +3 plus the square root of 3. Now what? We're not quite there yet. We're close. We're getting there, but not quite. We got a square root in the denominator yet. We got to rationalize this. How do I get that out of there? We got two terms in the denominator. Anytime you had two terms of trig identities, conjugate. Multiply by the conjugate in order to get it out of there. So we're going to multiply by 3 minus the square root of 3 in both the numerator and the denominator in order to rationalize that. All right. Numerator. Let's FOIL it out. Okay, let's multiply this out. So if I take the -3 and distribute, we get -3 times 3 gives you -9. When we take the -3 times the negative square root, it becomes a positive 3 square root of 3. Okay. If the number's not under the square root, it stays on the outside. Then we're going to take the square root of 3 and distribute. So positive square root of 3 times 3 is another 3 square root of 3. And the positive square root of 3 times the negative square root of 3 is negative 3. Because you're basically squaring it. Or you can think of it as a negative square root of 9, which is where the 3 comes from. Question, Nick? No? Okay. So when you distribute the negative 3 and then distribute the square root, here's what you end up with. The nice part, again, if you recognize the denominator as a difference of squares, when you multiply conjugates, when you multiply it out, here's all it multiplies to. Square the first term, square the second term, and throw a minus in between. It's a difference of 2 squares. So, first thing squared is 9. Second thing squared is 3. And then we have a minus in between. It's a difference of squares. Okay. First term squared, second term squared. Granted, if that doesn't make sense, you could FOIL out the bottom too. That's what you're going to get. Okay? The 2 middle terms will end up canceling each other out. All right, we're almost there. Let's clean it up. Negative 9 minus 3 in the numerator gives me a negative 12. 3 square root of 3 plus another 3 square root of 3. Those are like terms. I can put those together. That gives me 6 square root of 3s. Okay. Again, they act just like variables. 3x plus 3x would be 6x. Over 6. And what's the last thing I need to do to finish this off? Just simplify it. You can divide all 3 parts by 6. So we end up with negative 2 plus the square root of 3 as our final answer. That's why there's not a lot of tangent problems in the assignment. Okay? Because when you're dealing with tangents, you've already starting with a fraction, and then there's always fractions inside of fractions, and it gets messy in a hurry. Okay? Just take one step at a time. All right, last thing I have for you. This one I think you'll appreciate. This last part of the worksheet, I told you there's 10 questions on the worksheet. The last 4 are just like this. Where it's already written out, we're going to actually go in reverse. We're going to condense this. You remember back when we did logarithms and we were expanding or condensing? Well, this is already expanded if you think of it that way. We're going to condense this. We're going to make this simpler. First question I have for you, if we're going to try to write this as the tangent of one angle. When you look at your formulas, is this a tangent sum or a tangent difference? Okay. Yeah, if you take a look, specifically if you're looking at the sines, that's how you can tell whether it's a sum or a difference. When the numerator is added together, that is the sum. So this is really the tangent of the sum of 2 angles. And the 2 angles are the 2 angles in the problem. 165 plus 60. Which means if we just keep simplifying, if we keep condensing, what am I actually taking the tangent of? 225. Is 225 on the unit circle? Yep. What's the tangent of 225? 1. There's your answer. So the nice part about these, if we do go in reverse a lot of times and we try to clean it up, it turns out that we're going back to a unit circle value, which makes it a lot easier. Okay. And like I said, 4 out of the 10 problems are these types of problems on your worksheet where you are working in reverse, and it should simplify. Okay? Anybody have any questions? Today we're just going to kind of work our way through these different things and practice, and I'm going to give you the rest of the time. You got about 15, 20 minutes of class time. I'll hand out the worksheet, and you can work your way through it and see how much you can get done.